Hello, here in 2.7 we're going to study the precise definition of a limit, and what helps is to revisit what the intuitive definition that we were using before said. And to remind ourselves, if I were to write the limit as x approaches a of f of x equals L. Before, what we said is that this means that f of x can be made arbitrarily close to L, as long as we take x sufficiently close to A. So, thinking of the picture, I've got some function, say A is some point here. The limit as x approaches A would be just what the function values seem to be getting close to as x gets closer to A. And in this case, we can imagine that it will go roughly where this hole is. All right, and here I'm putting a hole in the graph to remind us that the point at A may or may not necessarily exist. For instance, if I do have a hole at A, the limit will still exist. Nowhere in this definition does it require that f of A exist. Okay? So what is a little bit fuzzy about this definition is what we mean when we say close. So that's going to be essentially what our goal of this section is to be a little bit more precise about what we mean when we say close to L or close to A. And so we'll have to use some more technical language to be a little bit more precise by what we mean when we say f of x can be made arbitrarily close to L, or x is sufficiently close to A. We have a notion of closeness that in this case will rely on thinking about the distance between those two values. So we're going to have to come up with ways to express the distance between f of x and L which we can imagine here is just looking at if I were to, for instance, close in on this point around L, the distance between f of x and L will kind of narrow down to a little window that we're going to build around L. So we want to come up with ways to express the distance between f of x and L in a more technical way. And similarly with the distance between x and A. In other words, what values of x here might correspond to the values of f of x that we're using to build a little window around L. Okay, so in other words, let's start to think about the range of values that go around x and the range of values that go around a, and then the range of values that go around L, where if we are going to make f of x close to L, then there are certain x values that satisfy that desired closeness. And to start to think about the language that we're going to be using here, let's consider a statement like this. The absolute value of f of x minus L is less than 0.1 whenever absolute value of x minus a is between 0 and delta. And this is the language that we're going to use to describe exactly what we were saying before. The distance between f of x and L we can express here by the absolute value of f of x minus L. And then here, the same idea, that here the absolute value of x minus a is referring to the distance between x and a. So a statement like this we can read as saying the distance between f of x and L is less than 0.1 whenever the distance between x and a is less than delta. And why is this an important notion to think about? So for one, we were trying to find a more technical way to express the notion that f of x can be made as close to L as we want whenever x is sufficiently close to a. So in this case, suppose we want f of x and L to be within a distance of 0.1 from one another. Then we should be able to find a distance delta so that x and a are within a distance of delta will guarantee that f of x and L are within a distance of 0.1. Okay, so that's how we're going to interpret it, is that if x and a are within delta distance of each other, then f of x and L are within 0.1 of each other. Okay, so that's essentially what we're trying to say is now, okay, if I wanted to get it even closer, then we could hopefully find a delta in that case as well. And so when I, for instance, change the value here to 0.001, then we're essentially just saying, okay, well, let's make f of x and L even closer. Okay, so what this statement is saying here is that whenever x and a are within delta distance of each other, right? That's what this symbolically is saying here. Whenever x and a are within delta distance of each other, f of x and L are within a distance of 0.001 of each other. Okay, so graphically, let's just kind of try and picture this really quick. Suppose here is a graph. And we can imagine what we're doing is we're saying f of x is within a distance of 0.001 from L. So let's just imagine I go a little tiny distance out, so it's kind of exaggerated here a little bit for the sake of being able to draw it, but we go out a certain distance, say 0.001 above and below. Well, then that's going to correspond to some values of x over here on our graph. And so this kind of builds a little window around L where we can find some corresponding x values that guarantee that whenever x is within this window here, then f of x will be within this epsilon, or I should say 0.001 window around L. So we can imagine here there are some values, say maybe a little bit tighter even, so that if a plus delta on this side or a minus delta on this side, if we're in the little delta window around a, then we're always guaranteed to be inside of this little 0.001 window around L. So to be a little bit more general now, we can say, suppose that I want epsilon to be any positive value, so it could be any big or tiny positive value. And generally we're thinking of it maybe being a really, really tiny value. So I can be really, really close to L. And oh, and that's actually what should be here. This should be epsilon over here. So that for any epsilon greater than 0, we can find a delta such that f of x minus L is within a distance of epsilon whenever x minus a is whenever x is within a delta distance of a. Okay, so how do we interpret this? So f of x in L can be made any distance of each other. So epsilon here can be any positive number. So f of x in L can be made as close to each other as we want. So don't repeat myself. Can be made as close to each other as we want. And we can always find a delta. And we can always find a delta, which is, in this case, a distance between x and a. So we can always find x values around a so that f of x is within that distance. Okay, and essentially that is how we can formalize that rather intuitive version that we had before, where we kind of roughly defined closeness to mean, okay, we're just getting closer and closer to the value. But now we're being a little bit more specific, that what we really mean is that epsilon and delta can represent sort of arbitrary distances. Well, epsilon in particular is an arbitrary distance, And then I can always find a delta to go with that particular distance that guarantees the function values are within that distance.